Hi everyone, and welcome back to the class on the practice and pitfalls of studying organic reaction mechanisms. We're on lecture 2 now, and this time we're talking about isotopes and isotope effects when it comes to studying reaction mechanisms. This is a subject very close to my heart. I spent much of my PhD looking at isotope effects. And in this brief introduction to the lecture, I wanted to tell you once again that we have to be quite limited in the lecture in what we talk about. I've focused mainly on deuterium isotope effects, and within that, kinetic isotope effects. This is a whole world into itself, and we could spend an entire lecture course looking at isotope effects on their own. But as with all the lectures, I'll link you to more information above and beyond what the lecture itself gives you. But in a shorter video, without further ado, I really hope you enjoy lecture 2 on isotopes. Hi, and welcome back to the course on the practice and pitfalls of studying organic reaction mechanisms. We're now on lecture 2, and this time we're examining kinetic isotope effects. To give you a brief overview of the lecture, we will first cover some of the fundamental concepts of studying kinetic isotope effects. Then we'll look at how these isotope effects can be applied in mechanistic investigations. To end the lecture, we'll cover some applications of kinetic isotope effects in the total synthesis of natural products. So let's get started at the beginning and look at some fundamental concepts of studying kinetic isotope effects. What is meant by a kinetic isotope effect, or KIE? KIEs occur when a specific hydrogen atom in a molecule is replaced by deuterium D or tritium T, and that causes a change in the rate of reaction involving that molecule. Correct interpretation of a kinetic isotope effect measurement helps uncover the nature of the rate-limiting step in a given reaction. Formally, the KIE is given as the ratio of rate constants, not rates, such that the KIE is equal to the rate constant of the undeuteurated reaction divided by the rate constant of the deuterated reaction. Take a look at the two reactions on the left of this slide. The top reaction is the acid-mediated bromination of acetone. If we compare the relative rate constants for the reaction using non-deuterated acetone and the alternative reaction using deuterated acetone, we see that the non-deuterated substrate reacts with a rate constant 7 times greater than that for the deuterated acetone. Because the two reactions are run under otherwise identical conditions, concentrations, temperature, etc., then it's also safe to say that the non-deuterated acetone has a reaction rate 7 times higher than the deuterated analogue. The KIE for this reaction is therefore 7.0. As an aside, if you're still a little confused about rates and rate constants, this is a good point to jump back to slides 10 to 13 in lecture 1, where we went over the effect of rate constant on the actual rate of both first and second order reactions. Rates and rate constants are not interchangeable terms. So coming back to this slide, look now at the bottom reaction. Here we see a base-mediated elimination reactions to form a styrene. Similarly, as in the case of the top reaction, the non-deuterated substrate reacts with a rate constant that is about 7 times greater than that for the exact same reaction using the deuterated substrate in place of the non-deuterated analogue. The substrate in this case being 1-bromo 2-phenylethane. The KIE in this case is 7.1, so very similar to that for the top reaction. To begin to understand what the KIE values mean for these reactions and beyond, let's turn the previous slide into a question. Given the KIE data for the bromination and the elimination reactions, can you propose a rate-limiting step in the mechanism for these reactions that is consistent with the KIE data given? If you want to give this question a go, pause the video here and come back later for the answer. So here are some thoughts on question 1 from the previous slide. Let's look at the top reaction, the bromination first. In this case, the methyl groups on acetone were either labelled with deuterium or not. Given the massive impact of this isotopic labelling on the observed rate constants for the bromination, it's reasonable to hypothesise that the rate-limiting step, i.e. the slowest step, of the reaction involves the CH or CD bonds in these methyl groups. A reasonable rate-limiting step in this case would involve the deprotonation of the methyl groups on protonation of acetone to form the enol, before bromination itself occurs. In the bottom reaction, the elimination, the labelled position was again the cause of a massive difference in the observed rate constants for the deuterated and non-deuterated molecules reacted under otherwise identical conditions. The rate-limiting step in this case is likely to involve the E2 elimination event, where the CH or CD bond is in an anti-periplanar relationship with respect to the carbon-bromine bond holding the bromide leaving group. Note that it is the rate of reaction and rate constants that change when we observe KIEs. The mechanism itself stays the same. It just proceeds at a different rate depending on the isotopes present. Finally, we have to note some other assumptions about studying kinetic isotope effects, and you can see these on the right hand side of the slide. Assumption number 1, isotopic labelling replacing CH for CD in our examples does not affect the potential energy surface or electronic states. Assumption number 2, only mass-dependent properties are affected, most importantly, vibrational frequencies. Let's look at some more examples now, with some more questions for you to try. The top reaction on the left of the slide is a base-mediated orthoiodination of phenol. When we run the reaction with and without deuterium labels on the aromatic ring, we see that the non-deuterated reaction has a rate constant about 4 times greater than that for the deuterated version. In the bottom reaction, we see the nitration of benzene. In this case, curiously, we see that the ratio of rate constants for the non-deuterated and deuterated benzene substrates in the nitration is 1.0. Both rate constants are the same. There is no kinetic isotope effect. For question 2, as with question 1, can you propose a sensible rate-limiting mechanistic step for each reaction that is consistent with the data provided? If you want to give this question a go, again, pause the video now and come back later to have a look at the answer to question 2. If we now look at the answer for the iodination of phenol, first in the series of reactions we've just presented, because the KIE was observed, we could suggest that the rate-limiting step involves the re-aromatization of phenol after the initial iodination event. This is consistent with the observation of a KIE. Our answer involves the breaking of the CH or CD bond, the initial iodination event, where the aromaticity is broken when the aromatic ring attacks as a nucleophile towards the electrophilic iodine. That does not involve such a process. You might say, but wait, that initial iodination event might not involve the making or breaking of a CH or CD bond, but it does involve the rehybridization of those positions. Doesn't that matter? Wouldn't that be the cause of a kinetic isotope effect? Well, my answer to you is that you would be right. Rehybridization can matter in such reactions, but it's not enough to explain the magnitude of the observed KIE of 4.1 in this particular reaction. We'll come back to this point about KIE magnitude in a later slide. In the case of the bottom reaction, the nitration of benzene, there is no KIE observed. Therefore, we could suggest that the rate-limiting step in this case is the initial electrophilic attack of the nitroxide ion on the benzene ring. This is consistent with the observation of no KIE because this step does not involve the breaking or making of a CH or CD bond. In summary, kinetic isotope effects are largest when the rate-limiting step involves bond making or bond breaking with the isotopically labelled atom. If the isotopically labelled atom is not involved in the rate-limiting step, no kinetic isotope effect, or indeed a much smaller secondary kinetic isotope effect, is observed. Again, we'll come back to the issue of KIE magnitude later. As mentioned already, kinetic isotope effects can be classified according to their magnitude and whether or not they are linked with a bond forming or bond breaking event. For a primary kinetic isotope effect, the isotopically labelled bond is made or broken in the rate-limiting step. A secondary KIE occurs when the labelled bond being made or broken is not involved in the rate-limiting step, but the isotope does indirectly affect the rate-limiting step or a less significant step in the overall reaction mechanism. A normal kinetic isotope effect occurs when the KIE is greater than 1, when the non-deuterated reaction has a higher rate-limiting rate constant than the deuterated analogue. An inverse kinetic isotope effect occurs when the KIE is between 0 and 1, when the heavier isotope, for example deuterium, reacts with a higher rate constant in the rate-limiting step than lighter isotope, for example hydrogen, H. Quantum tunneling effects not covered in this course can lead to kinetic isotope effects much greater than 8. The scale at the bottom of the slide gives you a visual idea of the normal expected range of hydrogen-based kinetic isotope effects. Remember too, whilst the absolute numerical scales will differ, these listed terms apply to all kinetic isotope studies, not just for hydrogen isotopes. In this lecture, we are simply focusing on hydrogen isotope effects because they are the ones most commonly employed in mechanistic studies. We turn now to the origin of kinetic isotope effects. In the diagram on the left of the slide, we see the standard Morse potential for a chemical bond, with internuclear distance on the x-axis and system energy on the y-axis. At the bond equilibrium position, R along the x-axis, at the base of the electronic potential energy well, minimum on the y-axis, the lowest vibrational energy level therein represents the 0 point energy, and this is highlighted in red on the slide. Vibrational energies E subscript n are dependent on the bond stretching frequency nu, which in turn depends on the reduced mass of the two connected atoms mu. The key equations on the right side start with Hooke's law at the top of the slide. Hooke's law shows the relationships between vibrational frequencies, force constants or spring constants k, and reduced mass mu, where c is the speed of light. It describes the properties of the force or spring holding the masses or atoms together. The equations for reduced mass and for successive vibrational energy levels are also shown in this slide. 99.9% of CH bonds are in the vibrational ground state, n equals 0 at room temperature. If we now look at the right side of the slide and to the reduced mass term for various isotopic pairs, we can see that the difference between the reduced masses for CH and CD is the largest difference, almost double in fact, of any atomic pair where only one isotope changes. If we look back at Hooke's law and see where reduced mass is placed in the equation, you can see that the effect of doubling mu on the denominator, going from carbon 12H to carbon 12D, is going to have a much bigger effect on stretching frequency nu than the more minute changes for other isotopes, for example carbon 12H to carbon 13H. This is why deuterium kinetic isotope effects are the most widely used of any kinetic isotope effect. Larger changes in vibrational frequencies mean larger changes in bond strength, and that in turn means easier to measure and record experiments than the subtler isotope effects. The graph of reduced mass versus vibrational frequency paints a clearer picture of why larger changes in reduced mass lead to isotope effects that are easier to measure. When you use the graph to visualize the difference in vibrational frequency delta nu for carbon-12H and carbon-12D, you can see an appreciable change in the y-axis. Compare this to a similar graph plotting carbon-12H and carbon-13H. This time the y-axis change is tiny when compared to the previous graph. Let's return to the Morse curve with a focus on carbon-12H versus carbon-12D. At the top, we can now see the differences in IR stretching frequencies and 0-point energies that derive from our previous discussion on reduced masses. This model for looking at deuterium isotope effects assumes that the CH or CD bond is fully broken at the transition state. At the transition state itself, what was a bond stretch is now a translation. Therefore, no new stretch at the transition state corresponds to the ground state bond. In this simple case, 0-point energy entirely dictates reactivity differences of isotopomers. Let's now take this concept one step further. In most reactions, the bond of interest is not fully broken at the transition state. Rather, it is only partially broken, and thus the transition state structure has its own 0-point energies. Consider the hypothetical deprotonation of AH by B. Here are some important points to consider. Point 1. The AHB system in the ground state defines the reaction coordinate and is primarily a stretching frequency. Point 2. Bending modes have much lower force constants than stretches and consequently contribute less to an overall primary kinetic isotope effect. And point 3. The proton is shared between A and B in the transition state. AHB creates a new symmetric stretch that has no analogue in the ground state. So, rather than simply comparing the differences in 0-point energies for carbon-12H versus carbon-12D in the ground state, we need to consider the difference of differences in 0-point energies between the ground state and transition state. This updated model enables us to consider 3 scenarios for kinetic isotope effects, shown in the diagram. Before we consider each case, we need to revise the Hammond postulate. This states that a transition state structure most resembles the structure it is closest in energy to, be that the starting materials or the products. Looking at the first case, on the left of the diagram, this exothermic reaction, reading left to right, has an early transition state. The transition state structure is therefore most similar in structure to the starting materials than the products. Crucially, this results in the ground state and transition state possessing similar differences in 0-point energy for CH versus CD. In other words, the difference of differences, delta delta ZPE, is small. Ultimately, this means that there is a small kinetic isotope effect. In the centre, a similar case is presented for the scenario of an endothermic process reading left to right. This time, the transition state and product energies are most similar, meaning the structure of the transition state is most like the products. Again, the delta delta ZPE is small, and any resulting kinetic isotope effect is also small. The most interesting case is presented on the right, for reactions approaching thermal neutrality. In this case, the transition state structure is not similar to either the starting materials or products. This results in a larger delta-delta ZPE between the ground state and transition state on either side of the transition state. It is in such cases that the largest kinetic isotope effects are present. Moving beyond the fundamental concepts needed to understand kinetic isotope effects, we will now look at some applications of these isotope effects in mechanistic investigations. Let's return to our earlier example showing representative kinetic isotope effects in elimination reactions. For the E2 reaction shown, the largest kinetic isotope effect, greater than 1, can be interpreted as a normal KIE involving breaking of the CH and CD bond at the rate limiting transition state. Conversely, the E1 reaction presented a much smaller KIE, still greater than 1. In this alternative case, the result can be interpreted as a normal secondary KIE resulting from hyperconjugative effects. Overall then, only E2 reactions involve bond breaking or making with CH or CD bonds in the rate limiting step. Practically, what we are seeing here is that kinetic isotope effects can be used to distinguish between mechanisms, in this case between E2 and E1. For the E1 case, presenting a secondary KIE as a result of hyperconjugation differences, the longer CH bond is most effective in hyperconjugation and more effectively stabilises the emerging positive charge, a carbocation in the resulting intermediate, than does the CD bond. Whilst a CH or CD bond is not broken or made in the rate limiting step, hence the smaller KIE number, it still plays an important part. Remember that kinetic isotope effects are not affected solely by participation of isotopically labelled positions at the rate limiting step. The thermal properties of the reaction also matter. Again, reactions that are closer to thermal neutrality can lead to the largest observable KIEs. To take this idea further, consider the following series of E2 reactions in which we alter the leaving group. On moving from bromide to tosylate to trimethylamine, the primary kinetic isotope effects diminishes from 6.7 to 5.7 to 3.0 respectively. What we are observing here is the changing nature of the transition state for each E2 reaction in the series. As the most effective leaving group, bromide leads to a more distinct transition state, least like the products or reactants. By the time we get to the least effective leaving group, trimethylamine, the smaller KIE can be interpreted as a later transition state and more endothermic process than for the other two E2 reactions in the series. Moving from elimination to substitution reactions, we saw previously that SN2 reactions can present an inverse between 0 and 1 secondary kinetic isotope effect, wherein the deuterated methyl chloride reacts faster than the non-deuterated analogue. The interpretation of this effect is due to the sterically smaller nature of CD versus CH. For a nucleophile, the electrophilic carbon is less encumbered when the carbon is decorated with CD rather than CH. For SN1 reactions, a normal secondary deuterium kinetic isotope effect is observed. In the formation of the planar carbocation intermediate, the centre carbon rehybridizes from sp3 to sp2. This process is favoured by CH over CD bonds, meaning the non-deuterated reaction proceeds at a faster rate than the deuterated analogue. Going further, as the SN1 reaction approaches the first and most important rate limiting transition state, i.e. towards the carbocation, the out-of-plane CH bending mode weakens. In other words, the out-of-plane bending mode is lower frequency, i.e. lower energy, in sp2 versus sp3. The out-of-plane bend weakens as the reaction approaches their transition state, making delta ZPE in the transition state less than delta ZPE in the ground state, giving a normal secondary kinetic isotope effect. An easier way to remember this phenomenon is increase in P is favoured by D. And overall, the presence of a normal or inverse secondary kinetic isotope effect can be used to distinguish between SN1 from SN2 processes. Let's now look at another question that you can have a go at. The 6-membered N-heterocyclic carbene shown in the box was observed to insert into a CH or CD position on toluene. For isolated reactions employing either deuterated or non-deuterated toluene, a primary kinetic isotope effect of 4.0 was experimentally observed. Additionally, using methyl D1 toluene, a secondary kinetic isotope effect of 1.18 was recorded. Given this evidence, is the CH bond breaking event part of the rate limiting step for this reaction? If you want to have a go at this question before seeing the answer, pause the video now and come back once you've considered the question in your own time. Turning to the answer, with the evidence provided, we would say yes, the CH bond breaking event, the insertion in this case, is indeed part of the rate limiting step. The normal primary KIE derived from the observed difference in the absolute rates of deuterated versus non-deuterated toluene reactants is enough to answer yes to this question. However, the secondary KIE recorded from the intramolecular competition between H and D in toluene D1 tells us more of the story. The normal secondary kinetic isotope effect recorded from this experiment supports the model that significant rehybridization occurs at the transition state, and the increased planarity is favoured by H over D. The authors also present further evidence to support this mechanistic picture, and you can read that in the reference provided. Let's now bring the lecture to a close by looking at the practical application of kinetic isotope effects and the synthetic challenges of total synthesis of natural products. During the GAR group's attempts to synthesize various well-witindolone derivatives, a silver-catalyzed nitrene insertion reaction highlighted a challenging CH regioselectivity issue. You can see a simplified depiction of the key reaction at the bottom of the slide. In the advanced intermediate shown on the top left, the reaction targeted insertion into the red CH position, but was hampered by competing insertion into the blue CH position. This resulted in mixtures of products and, most notably, poor yields of the target molecule. To solve the problem, the authors played a clever trick using deuterium labelling and kinetic isotope effects. To minimise insertion into the competing blue CH position, the authors synthesised an analogue in which the blue CH was replaced with CD. Now, when the silver catalysed insertion process was run, the reactivity difference of the blue and red positions was made more significant, leading to the target molecule as the major product in vastly improved isolated yields. Whilst many more examples of this isotopic trickery exist, this example serves as a useful story in how deuterium kinetic isotope effects can be used for more than mechanistic investigations alone. That brings us to the end of Lecture 2, our introduction to using kinetic isotope effects in the studies of mechanism. In summary, We've learned that kinetic isotope effects arise from different physical properties of isotopes, with the main concern being differences in vibrational energy levels. We learned that primary kinetic isotope effects arise from differences in zero-point energies at the ground and transition states, and we termed this delta-delta ZPE. We also learned that secondary kinetic isotope effects arise from changes in hybridization and from hyperconjugation effects. We saw some examples of how these kinetic isotope effects provide powerful tools for investigating and differentiating various reaction mechanisms. Then, finally, we closed by looking at a practical example of how kinetic isotope effects can serve as a synthetic tool in really challenging and complex syntheses, in particular problems of solving regioselectivity issues. So thanks again for watching. I really hope you've enjoyed Lecture 2 on kinetic isotope effects, and we'll see you back here for Lecture 3.